Hello and welcome to an FPGA Vision lecture. In this series we have a look at a neural network implementation with an FPGA. And in a previous video I've shown you this structure where we have three input signals, red, green and blue value of a pixel. And from this information we want to detect certain colors. And we use three neurons in a hidden layer and one output neuron. The project name is NN for neural network, RGB, FPGA. And you find the link to the source code on our homepage. We also had shown you training of the network. And for this we use this script, NN, RGB, two categories. And this script determined this parameters for the neural network, which are floating point. And in this video, we want to show you how to use this information to design your circuit in VHDL for an FPGA. The block diagram follows the structure of the neural network. We have the three input signals, red, green, blue, and then we have three submodules for the three neurons of the hidden layer, plus another submodule for the neuron of the output layer. The neurons get the parameters of the training. So every neuron gets as an information the bias plus three factors for the three input signals of the neuron. And we have output processing. The output of the neural network is a value between 0 and 1. And we're doing color mapping. So if the output value is 0.5 or larger, we indicate this with a white pixel. In other cases, we have a black pixel at the output. So the output image shows us the mapping of the color. This structure is coded in VHDL, and the top level is called NN RGB, and it uses four submodules for the four neurons, which are coded in neuron VHD. Plus we have another submodule, control VHD, for delaying the sync signals that our video uses. Color mapping is coded directly in the top level. For the implementation of the neuron, we had the general information about the function in a previous lecture. We have a combination of several input values with the parameters theta and then the sigmoid function. And this structure can be translated into hardware. So here we have the inputs x1, 2, 3 with 8-bit. Then we have generic parameters for the multiplication, w1 to w3. We add them together and we also add the bias. Then we get a value where we choose 14-bit as a word width. This goes into a ROM where we have stored the sigmoid function, and as the output again we use 8-bit. The word width can be changed. So we have 14 bits here, but other values are possible, which gives a different resolution. The submodule neuron VHD follows this structure. We have the multiplications, we have an addition, and then we use a submodule for implementing the sigmoid function as a ROM. And here we have a MIF file with a memory content. The advantage of the hardware implementation is the ability to achieve high computing power. We need this because we have a video signal as an input. In our example, we use a 720p format with about 75 megahertz pixel frequency. So with 75 megahertz, you have a new input signal to process. We map algorithm and hardware structure. This means that all the computations are done in hardware in parallel. Therefore, our implementation is able to handle the required processing effort of 12 multiplications, 12 additions, 4 sigmoid functions, and the color mapping for every clock cycle. For the required clock frequency, our design uses several pipeline stages, and you could increase the number of pipeline stages and reach frequencies of about 200 or 300 megahertz without problem. We implement our design in fixed point, and therefore we have to convert the existing floating point parameters. As an approach, we use 5 decimal places for the parameters w1 to 3. This means we shift them by 5 bit. For the bias, we have to consider that the inputs x1 to x3 have 8 bit. So they have values of 0 to 255, but they correspond to values of 0 to 1. Therefore, we have to shift the bias with another 8 bit. This conversion is done by an octave script. We have the script from the previous lecture that calculates the floating point parameters. And then we have a script NN, convert fixed point, that calculates the fixed point parameters. And here are the values. The 5 decimal places are a design choice. You can use other numbers of decimal places, and you can also change the word width of the sigmoid ROM and compare effort and results. And here we have the VHDL code. This is our top level, so entity NN RGB. These are the inputs. We have a clock signal, switches, which we're not using here, and then this is the video input interface, so vertical sync, horizontal sync, data enable, red, green, blue input. And here is the output, sync signals out, red, green, blue output. Then we have signal declaration, and here are the neurons. So we have 0, 1, and 2 submodules for the neuron with a generic map, and here we supply the values we got from the octave script. So these are the values for the neuron in the hidden layer, and this is the next neuron, this is the next neuron. Here is the output layer again with the parameter from the octave script. This is the control block for delaying the sync signals. And here we have our output processing. So in this case, it's relatively easy. If the output is larger than 127, the result is set to everything 1. And this is the RGB value. So this is white. If everything is 0, result set to 0, then the output pixel is black. We will get a more complex output processing in another video, which will come later. But as a start, this is the output processing converting the result of the neural network into colors so that we can see what the neural network does. Here is the submodule for the neuron. Entity description with the generic values and the signal inputs, signal output. And yeah, you can have a look at the code for yourself. Here are the multiplications we have. And then we have a limiting before we go to the lookup table, which is invoked here. And then we have the output. So now we have completed the design in VHDL, and you can do simulation. We provide a test bench, and there's another video that shows you how to do simulation in VHDL. In this video, I want to look at the implementation of the FPGA and to try it out on our remote lab. And for this, we do synthesis. In the synthesis tool, we see the design files. Don't forget to include the assignments for the pin location. And then we can start synthesis. We provide a remote lab so that you can verify the result of the synthesis. You upload the binary for the FPGA, and we choose a test image from the video of the highway. Then the FPGA is programmed with the binary file, and you will see the output of the FPGA operation. And we use a snapshot that is different than the one that we did training for. And here is the output image. And you can see the FPGA is working as expected. The yellow sign on the road is detected and highlighted here in white. But also some areas that do not belong to the sign are detected, and you can improve this by training. But this is also a limitation of the approach, because only choosing the color to detect the sign might not be sufficient. Please note, in the user interface of the remote lab, you see static images. But this is a video signal with 60 frames per second showing always the same image. and the output is a snapshot of one output frame. You can also calculate the power consumption of the FPGA. Here at the top you see the core current and the supply voltage. The remote lab shows that everything is working as expected. So now you can do your own experiments. You can use the data we provided. You can use your own test images to generate another neural network. You can change the word width inside the neural network and see the effect of that modification. In a future video, we will also show you a more complex neural network with more colors to detect. So stay tuned. Thanks for watching.